on which the advantage of that is that we can really keep the same eta coordinate for the whole x range, right? Because we can say last time I think we used the eta goes from 0 to 100 or something, right? And if we stick to the x and y coordinate, we have no idea how to set up our coordinate in y. In the beginning, the y coordinate may be very small, right? In the beginning of the airfoil, the y coordinate has to be very, very fine. But at the end of the airfoil, the y coordinate can be very thick. Think of an airfoil is one case. Think of an airplane is rather extreme. The Reynolds number is very high, right? So in the leading edge or in the front of your nose, the boundary layer is very, very thin. It's like millimeters. And we are going to consider turbulent boundary layers at the end. But the boundary layer on the airplane is going to transition from laminar to turbulent pretty early on, especially if you're considering the fuselage. And at the end of the fuselage, the boundary layer is thick. It's like that. It's very thick. And it's very difficult to set up a consistent grid in the y coordinate to really capture that. That is why we transform into the eta coordinate, just as we are doing the similarity solutions. So we can keep the same eta equal to 0 to 100 to solve for the entire range of the equation. That saves computational grid points, but also saves stiffness, numerical stiffness in the equation. Because if you have y coordinates very, very packed near the wall, as you go to later stages of the boundary, your whole boundary is very large. There is a huge ratio between the size of the boundary layer to the small grid size, and your solution is going to become very stiff. Okay, so that requires us to perform this pretty it looks cumbersome, but like we are going to see, we can remove a lot of terms. So we have this change of coordinates in the derivative. All right. So this is partial x, partial y. How about partial y? This is another thing that is a little bit counterintuitive, right? Y and eta has been changed, but it ended up the derivative of partial y can just be scaled. It's just a scaled version of partial y, partial eta, because the other coordinate means the same thing. So partial y in this case, you can do this rigorously, but I'm just going to write it down. This times partial eta partial y, which is 1 over delta. All right. So these two equations are what we are going to be using to substitute into that. Now another tricky thing is,
question.
Yes?
Why is the x term not included again?
Why is the x term?
Because
you can add partial c times partial c, partial y, and partial c partial y is 0. Yes, so this is 0.